Hello, my name is Charles Camarda, and this is Lesson 4 of the Innovative Conceptual Engineering Design course, or ICED, or ICE methodology. Today, this lesson, Lesson 4, is totally devoted to failure. So we're calling it Failure 101, the importance of failure and learning in design. Two of the major themes of the ICE methodology are directly related to failure, and several of the other themes could be considered to be indirectly related to failure in several ways. That is, why the entire lesson is devoted to this topic and will serve as an introduction to failure and how it impacts several important areas of engineering and innovative engineering design: trying, failing, and learning from failure. We'll touch on teamwork, collective intelligence, and learning from failure, how to ensure a culture of tolerance to failure and risk, a psychologically safe environment, and lessons learned, learning, knowledge capture, creation, and validation. Be indirectly related to arrogance and critical thinking, and systems engineering, panning out and zooming in. These are the themes which will be addressed in this lesson. These are 5 of the 7 themes. Of course, the 2 failure-related themes are directly related, and it will touch on also systems engineering, panning out and zooming in, critical thinking, and using the human mind for what it does best, innovation, creativity, and determining patterns in data. And here is an outline for how we will be covering failure. We'll be understanding what failure is and why it is important. We'll touch on the fact that there's a spectrum of failure, from praiseworthy to blameworthy, understanding and learning how to fail, using techniques like intelligent fast failure, where we fail smart, fast, small, cheap, early, and often. We will illustrate this process by an example, in this case using the damage assessment team as a case study and how they were unable to understand and predict impact damage following the Columbia accident. We'll be using simple modeling and simulation and strategic experimentation and testing, and showcasing why that was important. One of the case studies we will use is development of a reusable cryogenic hydrogen tank for the single-stage to orbit SFSCEO X-33 vehicle. The learning objectives for this lesson are as follows. By the end of this lesson, students should be able to explain the importance of failure and how to ensure you develop a culture which tolerates and encourages the right kinds of failure. You should be able to classify the various types of failure and rank them on a spectrum ranging from blameworthy to praiseworthy. You'll be able to understand and explain how to fail effectively to accelerate individual and team knowledge growth, to minimize knowledge gaps, and to rapidly validate new knowledge and innovative solutions. Students will also be able to understand the difference between intelligent fast failure and slow dumb failure. And lastly, you will be able to compare, evaluate, and improve design effective strategies for failing smart, fast, small, cheap, early, and often. This is a quote from one of Dr. Henry Petrosky's books on engineering failure and design. The concept of failure is central to the design process, and it is by thinking in terms of obviating failure that successful designs are achieved. This was from his book, Design Paradigms, Case Studies, Case Histories of Error and Judgment in Engineering. I told you that failure would be indirectly related to this design, and this is how. You have to constantly be thinking of ways your particular idea or concept can fail. You have to always be objective as possible, especially when evaluating your own ideas, to identify and address all potential failure mechanisms early. Knowing how your ideas can fail, and the next step is to think of ways you can simply and economically obviate or avoid such failures using the operation and life during the operation and life of your idea. This is a figure from one of Amy Edmondson's articles on failure, where she proposes the idea of a spectrum of failure. That paper is entitled Strategies for Learning from Failure. Reading this article is one of your homework assignments. I highly recommend it. Dr. Edmondson states that not all of the failures are bad. Not all failures are created equal. In fact, many instances of failure is not only a good thing, it is necessary and required. She describes what she calls a spectrum of failure, which ranges from blameworthy or deliberate deviance to praiseworthy. At one end of scale, you have blameworthy, where an individual chooses to violate a prescribed practice or process. Inattention is next, and it occurs when an individual inadvertently deviates from specifications. Lack of ability is next, and it's described when an individual does not have the skills, conditions, or training to execute a particular job. Process inadequacy is when a competent individual adheres to a prescribed but faulty or incomplete process. Task challenge is when an individual faces a task too difficult to be executed reliably every time. Process complexity is a process composed of many elements, breaks. Let me go back to that. Complexity is a process composed of many elements, breaks, many elements. Oh, Jesus. Let me go back to this one more time. Process complexity, a process composed of many elements which breaks down when it encounters novel interactions. Uncertainty, a lack of clarity about the future events causes people to take seemingly reasonable actions that produce undesired results. Hypothesis testing, that's when an experiment is conducted to prove that an idea or design will succeed, fails. Exploratory testing, an experiment conducted to expand knowledge and investigate a possibility that leads to an undesired result. These are things that typically happen. Exploratory testing, hypothesis testing, these are things which typically happen when you're trying to construct knowledge and understand the unknowns or gaps in a problem, gaps in knowledge in a problem. There also could be many other examples that you could think of that you may add to this discussion, and we will discuss those throughout this course. Okay, next we are going to focus on ways to fail intelligently. Okay, by intelligently, I mean we can fail smart, fast, small, cheap, early and often, to learn as much as we can, as quickly as we can, as inexpensively as we can, and also the purpose of this is to close any knowledge gap about our ideas or concepts, to explore any and all potential failure mechanisms, and to mature those ideas and concepts as quickly as we can, so we can be sure, if we decide to select an idea, that is very high probability that that idea will be successful. I have mentioned the case of the Space Shuttle Columbia accident. You have watched some videos like this and were assigned some readings. This is a devastating example of an organization that did not learn from failure, did not know how to design experiments to validate knowledge and created a culture which was toxic, not psychologically safe, where people could not express dissent without fear of recrimination and possible damage to their careers and livelihood. This, in my mind, was not a failure of technology, more specifically foam. It was a failure of imagination. Creativity is imagination applied. Imagination happens before creativity. Imagination is the ability to conceive that which is not, to ask the question, what if? Although large pieces of foam, as you see here, were breaking off during launch of almost every shuttle flight, no one asked the question or was passionate enough about finding the answer to what if the foam hit a fragile piece of TPS insulation, as it did on STS-107. This is one example of what I call failing smart, failing dumb, slow, and infrequent and expensive. In order to understand whether or not the foam actually was the cause of the problem, the Columbia Accident Investigation Boards, one of the first questions they had to answer was what caused the accident to occur. In the accident investigation language, what was the proximate technical cause of the accident? All signs pointed to the foam debris strike. However, many people thought originally that the foam debris strike could not have caused the tragedy. What I am going to show you first is an example of a slow, dumb, expensive test or experiment. Unfortunately, NASA, Johnson Space Flight Center, Boeing, and USA teams were more interested in conducting a large, slow, expensive test in order to determine if a large piece of foam could really have been the cause of the accident. So they had a full-scale mock-up of the entire shuttle wing leading edge to prove that this large piece of foam could cause the accident. My estimates that this test of this size probably cost about $10 million. Took many months to set up, would use limited RCC, reinforced carbon-carbon wing leading edge spares that were in short supply, and have very limited instrumentation to gain knowledge about the test results. The experts initially thought that they needed only 6 strain gauges on this entire vehicle. Totally inappropriate and inadequate. There would have been, if they did that, there would have been no real data captured which could have helped us develop and correlate a real physics-based ballistic impact analysis. If we allowed these contractors in NASA to proceed, all that we would have learned after this one test was a binary answer. If that one test with a 1.67 pound piece of foam traveling at 545 miles an hour could cause critical damage, we would not have been able to validate our modeling and simulation methods, and hence if we wanted to vary any one of those parameters, for example, the size, shape, velocity, angle of impact, we would have had to have run another very expensive test. This is not the way to collect data and to construct knowledge. Also, because it took so long to create the experiments, it would have taken months before we were able to learn anything which could help us understand the problem. Instead of following the initial methods proposed by the contractors, we were able to convince the Columbia Accident Investigation Board to conduct a research program using intelligent fast failure and methods to gain a tremendous amount of knowledge about the physics of the impact problem we were trying to study. And we used a building block approach. Immediately, the folks at Glenn Research Center, under the supervision of now Center Director Dr. Woodrow Whitlow and led by Matthew Mellis, configured their ballistic gun at Glenn Research Center to start testing foam and RCC material. The team at Glenn was linked to the landing impact dynamics specialists at NASA Langley, and together with Boeing Philadelphia, they created a research program to rapidly gain sufficient knowledge to understand the physics of the ET foam debris impact to an RCC wing leading edge. They were able to do this in less than 3 months and for very little money. Because these tests were intelligent and inexpensive, we could design a program with hundreds of tests, vary lots of parameters, and correlate these tests with numerical models for impact failure using a building block approach. This is how research engineers attack such a problem. Taking a building block approach, testing the failure, and understanding how each element behaves. For example, the foam, the RCC wing leading edge, the silicon carbide coating, etc. Now I will show you the difference when you conduct an intelligent fast failure using a building block approach. The folks at Glenn Research Center conducted a number of tests using small foam samples and impacting on a load cell, as you see here in the upper left figure. We approached these tests as the means to get as much knowledge as possible about the damage from foam debris to an RCC leading edge by these simple, inexpensive tests. The first one shows we're trying to understand the behavior of impact of foam at ballistic speeds? What material models do we need to use to predict deformations, strains, stresses, and what failure theories do we need in order to validate that we can predict failure of this foam upon impact? Is there a difference in failure response of foam in vacuum or at ambient conditions? That was one of the questions the researchers had to answer, okay? Because the foam is fabricated by compressed gas, which basically inflates the foam. They're closed cell foam pieces, and when you launch the vehicle, it experiences ambient pressure surrounding the foam at sea level, and when it gains altitude, the temperature differences vary. And so would there be a difference testing at ambient conditions compared to what actually happens at various altitudes? And would we have to test for those conditions? We also had to understand the behavior of ET foam impacts to RCC materials that you see in the lower left corner of this figure. What material models do we use to predict deformation, strains, and stresses of the RCC target? And what failure theories would we have to use in order to accurately predict failure and damage to the RCC failure? We test the failure, we validate our modeling techniques, as you see, and then we use what we learned to predict full-scale impacts. In addition, instead of only using stick strain gauges on this full-scale test, we actually used, instead of using 6 strain gauges, we used a full field strain measurement technique so that now we can get a much better correlation with our full-scale test. And shown on the right-hand side, you see our prediction for a full-scale impact, simulating the test conditions, which was conducted prior to the test, accurately predicts failure that you see in the lower right-hand corner. And so you can see when we put this all together and the research scientists conduct their analysis of the full-scale impact test on the right-hand side, you notice that we can predict, they predict a very large damage, about 14 inches by 14 inches to the wing leading edge. We were able to conduct these tests prior to the actual full-scale test. And when we conducted the test, we is how accurately these scientists were able to
Will final 0, 5, 4, 3, 2, 1, 0.
So that's amazing, right? In only 3 months, with the right team and using the right experimental techniques, we were able to understand the physics of ballistic impact of foam to wing leading edges. And we could use that analysis to then predict different shapes of foam, traveling at different speeds, hitting at different locations of the vehicle, to calculate and predict the probability of potential failure of foam debris striking a wing leading edge. This illustrates the building block approach applied to understand foam impacting damage to RCC material and how we build and construct knowledge to understand and predict how the foam and the wing leading edge materials respond to ballistic impact, how an understanding of the material behavior and also of a material failure model can be used to then predict the onset and evolution of failure. How we then take the damaged specimens from the impact test and conduct non-destructive evaluations of each specimen using a variety of techniques shown on the right: ultrasound, thermography, x-rays, etc. And when we compare the NDE results with our numerically predicted results of damage, we can finally take these impact damage specimens and evaluate methods to repair the damage, then subject the specimens to simulated reentry heating conditions in small arc jet facilities to predict whether or not the repaired specimens would have survived Earth entry. This is what we call failing smart, fast, small, cheap, early, and often. Look at all the information we were able to obtain about these specimens, the damage tolerance of these specimens, and whether or not they would survive entry conditions using very inexpensive small tests. This highlights the importance of failure. So why is failure important? First of all, We learn so much more from our failures than we do from our successes. We learned so much about the space shuttle after the Columbia accident that I would say we learned more in the 2 years following the accident about the vehicle than the sum total of 20 years prior to flying the vehicle. We learned about mistakes and assumptions and analysis techniques we had been using for years to validate and verify that we were safe to fly, and we were not. More importantly, we learned how little we really knew about key failure mechanisms, which were the direct technical cause of the Columbia accident. What causes the ET foam to pop off in large pieces and impact the vehicle? Success verifies what we already know or think we know, whereas failure helps to teach us what we do not know. And as long as we fail correctly, smartly, and intelligently. Throughout this course, we will follow the philosophy of Confucius. I hear, I forget, I see, I remember, I do, I understand. We will be learning by doing, following a problem-based, phenomenon-based approach. Success can also breed arrogance. Failure, however, keeps us humble, or at least it should. Success can also lead to a cognitive bias called overconfidence bias. The overconfidence effect, or overconfidence bias, is a cognitive bias in which a person's subjective confidence in his or her judgments is reliably greater than the objective accuracy of those judgments, especially when confidence is relatively high. It is one example of a miscalculation of subjective probabilities. Continuing on with the importance of failure, success breeds failure. Something else we need to understand. Success can lead to confirmation bias, which is the tendency of a person to only look for and/or interpret data in a way that confirms a person's existing beliefs. Hence, that person tends to minimize disconfirming cues or results that discredit his or her beliefs. Success can also lead to recency bias, which is the tendency to believe that trends and patterns that we observe in the recent past will continue in the future. This can tend to make us complacent and react more slowly to warning signs of impending failure. As shown by this graphic, clearly there was a history of large pieces of external tank bipod foam losses during the Columbia accident. In fact, one such loss occurred a little over 3 months prior to the actual accident. You would think that if there was a recency bias, that people should have been more cautious. However, what I believe might have been happening in this case was what Diane Vaughan has termed normalization of deviance. Normalization of deviance is the gradual process through which unacceptable practice or standards become acceptable. As the deviant behavior is repeated without catastrophic results, it becomes the social norm for the organization. When the Columbia Accident Investigation Board finished their report, I believe there were a total of 28 prior incidents of bipod foam loss, like the kind that caused the Columbia accident. Remember, these were only cases where one of the astronauts was able to grab a camera after ET separation and photograph the ET with proper lighting conditions, etc. Further analysis of more data and photographs indicated there were at least 45 such prior occurrences. Next, we'll talk about determining the mechanisms for failure. By understanding all potential failure mechanisms and using a building block approach, and for rapidly assessing these failure mechanisms, fail and learn fast and furiously. It is very important to create an environment where failure is not only tolerated, it is expected. Langley Research Center's culture, according to James Schultz in his book, Crafting Flight. A quote from that book is that Langley's greatest gift was permission to try and try again until the mission was successful. Learning by repeated attempts may appear to be cumbersome, but failures indicated areas where further research was needed to improve the understanding of flight phenomenon. At Langley, the mistakes were just as important as the successes, for they sowed the seeds of future accomplishments. So this permission to try and try again is what I term permission to fail. The environment should encourage open discussion of all failures and lessons learned. This will be covered when we discuss leadership and high-performing teams, and it depends on what behavioral scientists and sociologists call psychological safety. In fact, I believe we should reward openness and risk-taking. In addition, with respect to intellectual property and protecting IP, I believe that we should be open and transparent and share ideas. However, we must be very certain that we recognize where the ideas come from, where they first originated, and give the inventor total credit and possibly work together to help evolve and optimize the ideas by sharing collective intellectual property and also by sharing in the rewards of a successful idea or design concept. Continuing with determining mechanisms for failure, I use the quote, "The devil really is in the details." And as we learned by panning out and zooming in, we start at the macro level and zoom in to identify root causes of failure. The Shuttle tile debond story was one such story where at the microscopic level, fiber bundles cause stress concentrations in the lower layer of the tile bonded to the RTV strain isolator pad. We will discuss that in a later lesson. What we found was the quick determination of this root cause led to the rapid development of a solution, which was to densify the lower surface of the Shuttle tiles of about approximately the lower 0.1 inches of the silica tiles. You need to list every potential failure mechanism, and it's important you look at your ideas objectively. Identify analysis and test plans necessary to identify and address all the potential failure mechanisms you can think of. Identify also all analysis and test plans that you need to mature the various concepts. And of course, you test the failure. You ensure the tests and analyses are intelligent. You get the most out of every possible test. Next example we will show, which illustrates the importance of failure and identifying failure mechanisms early, was the development of a reusable cryogenic tank for a single-stage-to-orbit vehicle called the X-33. Remember, we discussed how you construct knowledge. I'm not going to go through that. We discussed that in a prior lesson, but you go through a very rigorous process of understanding and constructing knowledge, which is very important in learning about a particular problem and what we do in order to identify potential failure mechanisms. We also learned the importance of using a building block approach in order to construct that knowledge, put that knowledge together in order to understand how the full-scale test article will behave. This figure shows one of the concepts proposed by NASA, an actively evacuated honeycomb core. One of the ideas that uses a special titanium alloy for the face sheets and core that would not be susceptible to hydrogen embrittlement. The metallic TPS would have been a superalloy honeycomb outer face sheet, an efficient fibrous insulation in the middle, and a lower temperature material such as titanium in the inner surface, the honeycomb core, and also the inner face sheet. The metallic TPS would be mechanically attached to a titanium cryotank, thus eliminating some of the restrictive thermal constraints that would have been necessary for a bonded TPS design. This would help make the all-metallic cryogenic TPS tank competitive, I believe, with the composite designs, which companies like Lockheed were evaluating and designing for. In addition, the evacuated honeycomb would provide a multifunctional thermal and structural role by acting as a cryogenic insulation. This would eliminate life cycle issues with other concepts that relied on a brittle cryogenic foam insulation and also had to be bonded to the tank wall and which would require another set of thermal constraints to the design. Other concepts which were variations of this evacuated core design included other materials such as polymeric composite materials, more conventional metallic hydrogen tankage, and other TPS systems. What we wanted to do was evaluate and predict what the differences in mass would be for these different concepts. One of the other cryogenic tank concepts we considered was composed of polymeric composite phase sheets and a composite honeycomb core. It was believed that by using composites, we could save considerable mass over metallic designs. Shown here are some of the details and photos of real test specimens and test facilities which were developed as part of a building block approach to address key potential design problems very early. This is a close-up of one of the Flatwise tension specimens, because one of the very fundamental failure modes for honeycomb construction is the separation of the honeycomb core from its phase sheets. For a cryogenic hydrogen tank design, a critical concern was that there could also be a leak of air or hydrogen into the honeycomb core, which could liquefy the air as it comes in contact with the internal phase sheet, which is in direct contact with cryogenic liquid hydrogen at about minus 423 degrees Fahrenheit. If this were to occur, the condensing liquid would cause a slight drop in pressure within the cells of the honeycomb and suck additional air into the honeycomb cavity and allowing it to condense. This process was called cryopumping. The liquid would be trapped within the honeycomb core, and then it would expand rapidly, exponentially, upon heating. For example, when the level of liquid hydrogen drops in the tank, and this increase in pressure would cause the honeycomb core to explode or delaminate. A typical test specimen is called a Flatwise tensile specimen, shown here, which were adhesively bonded or brazed or welded in the case of the metallics samples that we tested. They were about 2 inches square, and we pulled them apart in a uniaxial testing machine in order to measure the ultimate strength of the specimen and to record exactly where the failure occurs and how. Now, you have to remember that this test does not exactly represent failure due to internal pressure differences, which are caused by cryopumping. But it only serves as an approximation. Shown here are some of the failed honeycomb core specimens and core Flatwise tensile tests that were tested. We tested these specimens at cryogenic room temperature and elevated temperature. These tests were critical to determining the ultimate hot and cold bond strengths of the material and the material fabrication procedures used for full-scale honeycomb tank manufacture. These test specimens were used to evaluate many different materials, combinations of materials, and bonding agents for various portions of the trajectory under varying thermal and mechanical loading conditions. Shown here is what we call a ravioli specimen. This specimen was specifically designed to understand and test the feasibility of actually being able to evacuate honeycomb core and to be able to maintain that vacuum for the life of the vehicle, of the tank. These specimens were approximately 10 inches by 10 inches, and they included a ramped or sloped edge closure and metallic stem for actively evacuating the honeycomb core. This slightly larger test specimen was designed to include a conventional honeycomb core closeout and mechanism for actively evacuating the core. The primary purpose of this test article was twofold: to determine the feasibility of actively evacuating and maintaining a vacuum in graphite epoxy composite bonded sandwich panels, and to test several methods for monitoring leakage and/or ingestion of air or hydrogen into the honeycomb core. That is the capability. We were thinking about using these specimens, actively evacuating them, and using that capability as an integrated health monitoring system to identify when we had problems with any of the panels on the pad prior to launch. The sloped, flat closeout sections were also designed to explore an alternative means for mechanically attaching different structural panel sections together. Shown here is a cyclic and mechanical thermal load test machine that we developed. And this test fixture was designed to simultaneously apply cryogenic temperatures on the liquid side of the cryotank and elevated temperatures on the thermal protection side, at the same time that we would apply in-plane mechanical loads. It is very important to simulate the in-plane and combined cyclic loading histories in order to determine the life cycle performance and mechanisms for failure of this particular concept. Since the environment varies from extreme cold to warm, and the designs include brittle materials, it is also critical to match the actual environment and load conditions as closely as possible. Because as we say, the devil is in the details. And when materials are brittle and less forgiving, especially at cryogenic temperatures, very small imperfections or design details can lead to premature failure. In particular, thermal loads require a higher resolution finite element analysis to determine key stress concentrations. Also, internal tank pressures would tend to bow the tank walls so they would curve, and any compliant layers that were attached to those walls, such as the cryogenic insulation and the bonded thermal protection system. During the early phases of reusable launch vehicle selection process, one of the contractors, Rockwell International, proposed an idea that was a derivative of the Shuttle orbiter design for the hydrogen tank and insulation. The idea was to bond closed-cell cryogenic foam insulation to the external surface of the aluminum tank, much like you have on Space Shuttle, and then to bond directly onto that foam, that cryogenic foam, the silica thermal protection tiles currently used on the orbiter. The contractor had conducted numerous tests in a facility very similar to this, in plane, directly in line, as shown above, and all specimens designs, their specimens survived multiple loads, many times the expected life cycle expected for the reusable cryotank. One small but very important detail was omitted in this test: the simulation of the pressure pillowing of the cryotank. There was no curvature as the loading occurred. Once the contractor accurately incorporated the out-of-plane deformation the pressure vessel would see during real loading, it was soon realized that the brittle foam's low strain to failure caused unacceptable damage, and no increase in the density of the foam could sustain this ultimate failure. By recreating the critical failure mechanisms and designing intelligent tests early, you can evaluate many concepts quickly and inexpensively. So what actually happened was this entire design that Rockwell International was proposing for the cryotank, where you would bond a silica tile, which is very brittle, to the brittle cryogenic foam. If you did not include that pressure pillowing as you applied the cyclic load, so you were actually bowing and curving the cryogenic foam and the TPS, you would not have understood, you'd not have recognized that this was a critical failure mechanism. And no amount of densifying the foam or the TPS tile would have prevented that failure, because it had a very low strength to failure. It was a very low strength, a strain to failure material. This is another facility that we developed in this building block approach called the Cryogenic Pressure Box Test Facility. Because as we continue to build upon this building block approach, the next step is to look at applying combined in-plane load scenarios from both directions. We designed and had built this new test facility in order to do that, to validate this full-scale tank subsections under realistic static, thermal, mechanical, and pressure loads. Curved tank panel concepts can be tested in this facility at a relatively low cost to full-scale tank test in order to evaluate the feasibility of these various tank constructions, their attachment to TPS material, etc. We designed and had built a new test facility, the Cryogenic Pressure Box, or CPB test facility, in order to validate full-scale tank subcomponents under realistic static and thermomechanical and pressure cyclic loading conditions. Curved tank panel concepts can be tested in this facility at a relatively low cost compared to full-scale or scaled tank tests at cryogenic temperatures. Finite element analysis performed at Langley predicts the strain distributions developed during testing in the CPB, that they will be similar to strains seen in full-size cylindrical tank designs that can be produced in a 0.75 meter by 1 meter region in the center of the test specimen. The test of cycling with mechanical pressure and thermal loads on full-scale assemblies of tank walls with cryogenic insulation, thermal protection system, and integrated vehicle health monitoring can all be tested during the testing of a full-scale subcomponent. We could also look at manufacturing and fabrication details and refine them before we fabricate the full-scale design, thus reducing the risk of premature failure in a full-scale tank due to cyclic thermomechanical loading. Schematic section of the CPB is shown above. A view of the chamber is shown here. In this subcomponent test, a 1.5 meter by 1.8 meter curved panel is loaded in biaxial tension by internal pressure and mechanical actuators. In addition, both cryogenic and elevated internal temperatures and an elevated external temperature can be applied. The biaxial tension load is introduced into the panel by internal pressure, which is reacted through the load frame and by axial actuators. The maximum load applied to the actuators, not shown in the figure, is 2,000 kilonewtons or 450 kips. Circumferential or hoop loads due to pressurization are induced by the reaction force from the load frame through load introduction plates. The vacuum-jacketed pressure chamber can withstand internal pressures ranging from about 372 kilopascals using gaseous helium as the pressurization medium. Test panel and chamber can also be subjected to internal temperatures ranging from 250 Fahrenheit to minus 450 degrees Fahrenheit with the aid of 12 copper-heated exchange towers that are encircled by copper coils that contain liquid helium, gaseous helium, or liquid nitrogen. The gaseous helium is recirculated through fans in the heat exchanger towers. Helium does not liquefy at temperatures above 15 K and can be used to convectively cool the specimen and the CPB. The heat exchanger towers also have resistive heaters at their bases, enabling internal heating of the chamber and internal surface of the panel to a maximum of 395 Kelvin, 250 degrees Fahrenheit. Cont's lamp heater array is also used to heat the external surface of the specimen to maximum temperatures of 1,000 degrees Fahrenheit. The heater array is flat and has 8 symmetric zones that can be individually controlled to evenly heat specimens of various curvatures. In 1994, NASA initiated the Reusable Launch Vehicle Program, or RLV program, with the purpose of designing a more affordable way to launch payloads into space. NASA invested several RLV concepts and decided that a single stage to orbit concept offered the best solution. The X-33 vehicle was proposed as a subscale technology demonstrator program, which would advance several key technologies necessary to advance the reusable single stage to orbit dream. The Lockheed Skunkworks was the contractor selected and went on to design their vehicle that they called the Venture Star, which is shown here. There were several key technologies that needed to be matured in order to make this dream possible. One of them was a linear aerospike rocket engine. The other was durable metallic thermal protection system. And the last technology was a fully reusable graphite epoxy hydrogen tank and oxygen tanks. Now, the design for the Lockheed cryogenic tanks for hydrogen was a very complex multi-lobe design, and it was designed that way so that it can fit efficiently within the aeroballistic shape of the vehicle. And it was a graphite composite honeycomb sandwich construction. The facilities and test articles described previously were designed for an evacuated honeycomb cryotank, which was proposed by NASA for the reusable single-stage to orbit vehicle. One major difference between the NASA tank design and Lockheed's was the fact that NASA's design required an evacuated honeycomb to prevent possible cryopumping of liquid into the honeycomb core and subsequent rapid internal pressure rise upon heating of the structure. Lockheed's concept did not follow the building block approach which we outlined as part of the ICE methodology. They did not explore all potential failure mechanisms of the cryotank prior to designing their full-scale test article, which you see here. This full-scale test article was to be their proof of concept test. It was large, it was expensive, and it was difficult to manufacture, and as a result, the final design of it occurred late in the product development part of the program. The failure of this tank late in the program resulted in the entire cancellation of the X-33 program. It was a shining example of what not to do and is the reason for the development of advanced product development strategies, which we will present as part of the ICE methodology at a later lesson. We call these strategies rapid concept development, and they use many principles of set-based design. Shown here are the pressure measurements inside the honeycomb core of the X-33 tank during one of their tests. After successful completion of the first prototype pressure and loads test, the tank was drained and purged, and a purge of the tank began. Approximately 15 minutes after the tank was drained, the outer phase sheet core of lobe 1 separated from the inner phase sheet. You notice that the internal pressure rises exponentially after the tank is emptied, as shown here. The most likely cause for this pressure rise was that somehow nitrogen and/or air infiltrated the honeycomb, liquefied within the cells after coming into contact with the cryogenic inner phase sheet, and once the tank was drained, the temperatures rose sufficiently so that the trapped liquid rapidly evaporated and internal pressures rose very rapidly. This process of liquid formation being sucked into the honeycomb was previously known to the test team. In fact, they were alerted to this potential critical failure mechanism very early in the development of the program by the NASA team. We determined this was a problem because we had a very difficult time trying to actively evacuate composite honeycomb tank designs when we were using our ravioli test specimens. The reusable launch vehicle program wrestled with the complex multi-lobe composite tank manufacture. Especially difficult was the metallic joint required to join two lobes of the composite cryotank. Issues with the composite phase sheet microcracking and hydrogen permeation into the core also became a very difficult problem for the team. The structures lead for X-33 would not listen to review members' recommendations concerning potential cryopumping problems with the non-evacuated design of their concept. The failure shown here was the result after several years of hard work. Microcracking of the phase sheets allowed gaseous hydrogen to slowly permeate the honeycomb core during filling. Cryogenic temperatures either allowed the hydrogen to remain liquid within the cells or caused air or gaseous purged nitrogen to enter and liquefy by the process we identified earlier called cryopumping. Once the tank is drained during the test procedure or during boil-off during launch, the liquid level in the tank drops sufficiently, the trapped liquid hydrogen or liquid nitrogen vaporized, pressure within the cells rose, and the honeycomb skin blew apart, as shown here. As Henry Petrosky warns, neglecting details, not recognizing all the potential failure modes, and not designing to obviate failure caused this design to fail. I also believe the cause involved arrogance. of certain program leads who failed to heed the warnings given during the early design reviews, where this exact mode of failure was pointed out as a potential problem. And this is another view of the failed cryotank, and below is a link to the report of the Cryotank investigation team. What the team found out was that one of the primary causes, besides the proximate technical cause of this particular failure, was the fact that the team did not use a building block approach, as indicated in the upper left-hand corner, and what we prescribe in the ICE methodology. Okay, here we're going to talk about some of the lessons learned from this case study. First thing we're going to talk about is conceptual blocks and paradigm shifts. We all have conceptual blocks which form of our own personal thinking, which constrain the way we process information, construct knowledge, and link knowledge constructs in order to analyze complex information and make decisions. There's a good book called Conceptual Block Busting, A Guide to Better Ideas by James Adams about this concept. One such conceptual block is the thought that because composite materials are typically lighter than metallic materials, that one way to propose a lighter weight cryogenic design would be to manufacture a composite cryotank. However, if we open up our design space and pan out to include not only the cryotank but also the thermal protection system involved in this system, it is easy to see that we can arrive at an optimum design of a metallic tank which may be just as light or very close to the weight of a composite cryotank. We also need to remember to zoom in to address all potential failure mechanisms in a building block fashion, just like the potential honeycomb leakage and cryotank pumping problem of the X-33 tank. So now we're going to talk a little bit about how we expanded this design space to include not only the cryogenic tank, but also the thermal protection system, and how we compared a metallic tank to a composite tank. So we're including in this optimization, remember, as we're going through this analysis, experiment, and optimization loop, we're looking at many different ideas for minimizing the mass of this tank and TPS combination. We're looking at metallic tanks versus composite, aluminum versus titanium, and external ceramic bonded TPS versus metallic mechanically attached TPS. What became apparent was that when you looked at a cryotank as part of a larger system, which included the thermal protection system, added the temperature constraints for such a bonded system versus a mechanically attached system, the difference in mass for an all-composite ceramic bonded cryotank thermal protection system versus an all-metallic evacuated honeycomb core mechanically attached metallic thermal protection system were not that different. The lightest weight graphite composite honeycomb tank with a metallic superalloy TPS, which is mechanically attached, was found to be 16 kilograms per meter squared. The next lightest concept was an all-titanium evacuated honeycomb core sandwich tank with a mechanically attached superalloy TPS, which was 17.8 kilograms per meter squared, only 1.8 kilograms per meter squared heavier. When you consider the technology readiness level of making a leak-proof metallic honeycomb sandwich to contain cryogenic hydrogen versus a composite design, the decision becomes much easier to make. Shown below are the two references which describe the design process for optimizing this metallic TPS and metallic hydrogen tank design. Okay, this slide talks about some of the other lessons learned during this case study of the X-33 cryotank. Failure mechanisms. Once again, you need to objectively look at all critical failure mechanisms very early on and test them in an intelligent way to see if there'll be a problem. Another issue was arrogance. We warned the program several times about cryopumping, but they ignored our concerns. In addition, Lockheed Martin Skunkworks failed to pull in key people that they had from other companies like General Dynamics and Martin Marietta, which these folks had considerable experience in composite cryotank design. And I think this could partially be the result of arrogance on the high-level managers in the Lockheed Skunkworks. Next, here are some helpful tips to remember to help you in trying to obviate failures in your design. First and foremost, assume the impossible can occur and will occur as you're evolving your design. And then think about ways that you can obviate that failure. Use critical thinking when evaluating your ideas and when factoring in outside advice and/or information. We need to critically question all observations and key assumptions. Dig deep and remember to ask several whys in succession as you go through this process. We need to encourage and reward dissenting opinions. And we need to create an environment which is psychologically safe. We need to be wary of quick, what I call idiosyncratic explanations of failures, as more often than not, these are not normally accurate and they oftentimes obfuscate the real problems and issues. Beware of confirmation bias. Do not just report successes, also highlight any anomalies. Constantly study the lessons learned and the histories of past and prior failures. And lastly, seek the advice of experts and people that are external to your immediate group. Here are some additional ways to obviate failures. As we mentioned earlier, beware of recency bias. Strings of successes can lead to complacency and create an overestimation perception of knowledge and understanding about a problem. Just because anomalies did not occur in several prior runs does not mean that the probability of that negative event will have changed. Do not overly rely on analysis alone. Test often and test the failure to ensure your analysis is accurate and within the assumptions that you have made so that you can accurately predict when failures occur and how they occur. We talked about intelligent fast failure as opposed to slow, unintelligent failures, right? We have gone into detail of two case histories, ET foam, RCC impact, and the cause of the Columbia accident. And we also looked at the case study of the design of an X-33 reusable cryogenic tank. Both are very good examples which differentiate slow, stupid, expensive failures compared to what we are trying to teach in this course. A methodology that we prefer to use is intelligent fast failure. The initial proposal to conduct an expensive full-scale test of an RCC wing leading edge with minimal instrumentation and no physics-based analysis prior to test as compared to the debris assessment team's strategy, which used a building block approach. And lastly, the Lockheed X-33 reusable cryogenic program, which did not follow us intelligence fast failure building block approach strategy and which ended in a catastrophic failure late, which caused the cancellation of the entire program. In conclusion, here is a quote from Admiral Hyman Rickover, the father of the U.S. nuclear navy, the man responsible for creating the safe operation of nuclear resources to power submarines and aircraft carriers. What is needed is an atmosphere, a subtle attitude, an uncompromising insistence on excellence, as well as a healthy pessimism in technical matters, a pessimism which offsets the normal human tendency to expect that everything will come out right and that no accident can be foreseen and forestalled before it happens. In summary, we stress the importance of failure early in the design cycle, the importance of creating an environment which permits failure and stresses learning from failure, the importance of risk-taking and rewarding risk-taking, and the importance of psychological safety. I want to thank you very much. This has been Lesson 4 of the ICED methodology. Thank you.